Okay, we are in live.
Okay. Okay, good morning, everyone. So, this is Dr. Qadeer Khan. Okay, good morning, everyone. So, just hold on. So, Victor, am I supposed to? Because I am hearing my own voice. So,
Just mute the YouTube video link.
okay. So, Victor, okay. Okay, so as you all know, this is the live session for a PMIC and NPTEL course. So, looks like none of you have entered the questions, so I can take the live questions in the chat window. So, I mean, we can start right away.
Hello, Dr. Qadeer. It's me, Victor, on the other side. I just have two questions quickly, but the first question is regarding on the SOC side. So what I just want to know, your course material is very, very valuable, and it's very aligned with the way we worked on the industry. So I just want to know for the whenever, for an example, current mode or constant on time, and you talked about also voltage mode with the different compensation technique.
Yeah.
So when we are interfacing with the SOC, as SOC has also power demand or power hungry, and the load changes very frequently. So what are the parameter we need to consider for selection of the control method or the IC? So as a summary, yeah.
Yeah. So regarding the control method, I mean, broadly, if you want to categorize, I have categorized into linear and non-linear control methods. In the linear control methods, you have this voltage mode and current mode, and the non-linear, you have a hysteretic or constant on-time control. So the main thing you have to look into that whether you can afford any variation in the frequency, then obviously the non-linear would be a better because of the transient response. Better transient response compared to the linear method where you have your bandwidth is limited to 1/10 of your switching frequency. But if you cannot afford, for example, let's say you are powering a RF system. So in most of the RF system, you cannot even afford a small ripple due to EMI reasons, and there might be some EMI concerns with the fixed frequency current injected into the substrate. So there may be a radiated EMI or conducted EMI. So most of the time what we do, we prefer to have a fixed frequency, and once we know the frequency, it's easier to filter out that. So in most of the RF cases we use notch filter to filter out any particular frequency, EMI filter basically. So that would be easier to do. So but if you're not very noise sensitive, then you can right away go with the non-linear control, because it will give you a better transient response, and at the same time the control method, I mean the control loop, designing control loop is not as complicated as linear control because it doesn't require as such a big compensation network.
That's it. I mean, EMI is a good one trade-off you have mentioned. So that is a good selection parameter.
Yeah.
And another quick question on that regard. So for an example, on SOC, we have a couple of rails like 1.1 volt, 1.1 volt, multiple rails. We have the same voltage level, but different current rating. Like for an example, one rail is 1 amp, or other rail is 6 amp, and whereas other rail is 500 milliamp.
Correct.
So this is always a question in my mind, that how should I decide that, okay, which one should be LDO I need to pick, or which rail I need to pick for the
Yeah.
DC-DC?
So I think this particular topic also covered in, I mean, if you look at my first few lectures, how do we decide between switching regulators and LDOs? So the first thing you have to look into the basically the efficiency, the overall system efficiency. So you know, the LDO, as your dropout voltage is higher,
Correct.
your efficiency will of the specific LDO itself will be very bad. So
Bad
for example, let's say you are going from 1.8 to zero 0.9 volt, so you will lose 50%
efficiency.
yeah. But you have to you have to look at the other aspect, that LDO may be having a load current of, let's say, 100 milliamp or so, while on the
Mm,
other hand your switching regulator may be having a, let's say, couple of amps. So
mm,
comparing with the 100 milliamp, even if you have a 50% efficiency, but on the other hand, with the 2 amp current switching regulator, your efficiency may be of 90%. So impact on the overall efficiency will not be that big, because LDO is only powering very small portion of the total system power. So in that case, you can right away go with the LDO, even if the LDO efficiency is slightly lower. But if, let's say, you have a, maybe you want to have a LDO where load current is 2 amp, there the dropout voltage becomes a big concern. So
correct.
let's say your output rail is 1.6 volt and input is 1.8, so you'll be losing 200 milli volt there. So with 200 millivolt dropout, even if you, let's say, 1 amp kind of a current, the efficiency impact may not be that big compared to when your output was 0.9 volt with respect to 1.8 volt input. So you have to look both the aspects. So if you are going with a higher current, then LDO, you may prefer LDO for a lower dropout, because your efficiency will be comparable to your switching regulator, and on the at the same time, you know, the LDO will be cheaper compared to switching regulator, but it
Switching
doesn't
regulator.
require inductors. But if your dropout is large, but your overall power which is being catered by the LDO is very small, let's say maybe a 10% or lower of the total system power, then again you can consider even going for LDO for a larger dropout. So if you look at I mean, any PMIC which is used in cell phones, you will find maybe 40 to 45 rails, where number of LDOs may exceed number of switching regulators. So there may be, let's say, 8 to 10 switching regulators, but the number of LDOs may be 32 LDOs. And you may find that there are LDOs which are having a hundreds of milliamp current, but dropout voltage is 400 500 millivolt, because the overall impact on the efficiency is not that big, because LDOs are only powering a small portion of the total system power. And if sometimes these LDOs are also used as a sub-regulator for to filter the noise. So for example, we know switching regulator has some ripple in the output,
Switching,
and
yeah.
yeah, and you want to power let's say RF system with that, then if you use a high PSRR, so let's say your switching regulator is operating at 1 megahertz, and you are able to achieve 40 dB kind of a PSRR at 1 megahertz. So your 10 millivolt ripple will be suppressed by 100 times, and you will hardly see any ripple at the output. So that's another application. So for the sub-regulator, you always maintain a very low dropout. So for in that case, let's say my requirement is 1.8 volt. So I will basically program my switching regulator to have a 1.85 or 1.9 volt. So where your 50 to 100 millivolt kind of a dropout you can have at post regulator, which is your LDO, and your efficiency impact. There will be some efficiency impact, but it won't be that big. So you may lose maybe 2 to 3% efficiency there, but at the same time, you are able to achieve a very clean rail at the output of LDO, and you can directly power your noise sensitive systems.
Very valid. Got it.
Okay, any other question?
Hi, sir. This is Abhishek. Can you hear me? Hello.
So let me just, I think one question I received over email. So let me just
Hello.
answer that.
Hello.
Yeah, hello? Yeah, go ahead. You have any question?
Yeah, sir, I'm Abhishek. I shared a Word file to one of your TA.
Yeah.
So, has he shared it or shall I ask the questions? I had a few set of questions.
Yeah, just ask.
Yeah.
Mm,
Okay.
I
So
can answer
this question
directly.
is regarding battery charging, how
Mm-hmm.
battery charging profile.
Mm-hmm.
So when we are in a pre-charge mode, the current is like just in 1-2% of the what the full charge fast charge current is.
Mm-hmm.
And in that time, voltage is slowly linearly building.
Mm-hmm.
And when we suddenly increase whatever the fast charge current we are going, but there is no abrupt change in the voltage build up. Still, voltage rises linearly only.
Mm-hmm.
So my question is how that is achieved, or what we need to understand that, like
Yeah.
how. Yeah.
So first thing you need to understand how the battery is modeled. So a battery is modeled like a very big cap. Because battery is storing the charge, and the capacitor also does the same thing.
Yeah.
So if you have a very huge cap, if there is a sudden abrupt change in the current, your voltage is not going to change. There should not be any abrupt change in the voltage if it's a huge cap. The sudden change in the voltage only happen if you have a series R, the resistance ESR. uh, so most of the time battery is modeled with the big cap and a series R, where R is nothing but similar to what you have equivalent series resistance of any capacitor.
Yeah, like something like ESR.
Yeah, some ESR. So if that ESR is very small, the change in the voltage will be very small. So for example, let's say you are going from all the way from 100 millivolt and jump to 1 amp kind of current. And
Yeah.
if your ESR is, let's say 10 milliohm, so you will see maybe around 10 millivolt kind of a change, which is very small, minimal
Okay.
change in the output. But ESR is large, then you would definitely see a large step change in the output. So, but most of the time, it's not that ESR is not that huge that you will see maybe you won't see more than few tens of millivolt change in the output voltage. So 40, 50, or maybe at max 100 millivolt, not more than that. And sometimes even this is used to measure the ESR of the battery. So if you make the step change in the current, and the step change in the voltage, delta V by delta I will give you the ESR value. So in fact, this is used to this abrupt change in the current, what we call, is used to measure the ESR also, because that the final battery voltage will be the actual voltage plus IR drop across that resistor. So if I have to fully charge my battery, let's say up to 4.6 volt, and my voltage drop across ESR is 100 millivolt, then the 4.6 volt you will get at the battery voltage, uh, uh, I mean 100 millivolt before, which means even though your actual battery voltage is 4.5 volt, but because of this IR drop 100 millivolt, you will see that battery is fully charged, which is not true. So when you stop charging, then again your battery, you will see that IR drop will become 0 and battery will go back to 4.5 volt, and then again you will basically enable your charger. So, but if you know the ESR, then you know that you 4.6 in order to achieve 4.6 volt battery or 100% battery charge, you have to charge up to 4.7 volt. So because 100 millivolt drop is across that ESR. So in that case, you can fully charge your battery while being in constant current mode.
Okay.
Yeah, and you had a couple of more questions also.
Yeah.
Yeah.
So, and now one more thing is, you told actually you told that I will explain it in the video, but that I think that part was edited in the video. That thing was when we are getting a voltage from an AC adapter. Generally, the standard is 5 volt.
Yeah.
But now we are increasing it to 9 volt and also 12 volt.
Yeah.
So what is the reason for that, and how it is advantageous by doing that?
Yeah. So you need to understand two things. One is the standard USB, which you have the basically the data port, USB data port. So
Yeah.
your USB data port is still 5 volt, and your current, I mean, in USB 2.0, it was limited to 500 milliamp, and USB 3.0 now it's maybe 900 milliamp or up to 1 amp or so. So with the standard, the current rating is changing, but for data port, the voltage is still 5 volt. But when you talk about the dedicated USB charging port, then the standard is different for that. So for that, you violate the USB standard basically by changing this 5 volt rail to 9 volt or 12 volt. And that is, I mean, the main reason is why it is done is because so your USB that adapter, basically wall adapter, it's so let me just write here. So this is your wall adapter. You can see my screen, correct?
Yeah.
So this is your and here is your USB cable, correct? And now you have your phone. So USB cable has some resistance R. So it will have IR drop also. So if this is 5 volt, and let's say this cable resistance is 200 milliohm, 200 milliohm. And now if your charging current is, let's say this is your I charge. Three amp. So you will lose 0.6 volt drop here. So here it will look like 4.4 volt, correct?
Yeah.
So now 4.5 volt is below your minimum USB voltage which is required. So usually the spec is 5 volt plus minus 5% kind of thing. So the moment you go for below 4.75 volt, that may not be sufficient to basically operate your circuitries. So that will you are basically hitting the USB under voltage. So you can never charge. But now if let's say you make it 6 volt, then this will be 5.4 volt, and the maximum USB voltage is 5.5 volt. So you are still within your spec, and now you can charge your phone with the 3 amp. So one of the reason to increase the voltage is to compensate for this IR drop. Correct?
Yeah.
So at the same time, now if you keep increasing the voltage, and then for the same output voltage, the input current which is drawn from this cable will be lower, correct? So for example, let's say I make this, let's say I'm drawing a 3 amp, my charging current is 3 amp, and output current basically, and you are very close to, let's say your battery voltage is very close to USB voltage. So which means your input voltage will also be very close to 3 amp when you are nearing the full charge, because that time your duty cycle will be close to 100%. Now, if I make this 5 volt to 10 volt, then the required duty cycle for the same voltage will be 50%. Correct. So
Yeah.
and the input current will also drop by 50%, which means the input current drawn will be 1.5 amp. So now if you look at IR drop, that will be only 0.3 volt. Okay. So by doing that, one thing, you are able to do the fast charging. At the same time, you are able to reduce the I square R losses through this cable. So your efficiency will also go higher. So, so that's the main reason for the fast charging you do with the higher voltages. And now if you go to the USB PD, which is your type C, so now even with the tablets and laptops, you are getting the same port. So now we are going with the common standard across all the devices, so that you don't have to use a different, if you remember, let's say maybe 7, 8 year or 10 years back, when you used to have a cell phone, different cell phones had a different charging port. So if you have a, let's say in the family 4 members, all 4 will be using different chargers. Correct. But nowadays, a single charger can maybe charge multiple phones if it's has a standard USB charger. So, so with the USB PD, now even your laptop charger can charge your cell phone. So if you have a Type C connector, you connect it. So laptop requires, let's say 15 volt or so, because your battery is a higher voltage in laptop. The moment you connect the cell phone, your battery is so in laptop your battery may be, let's say 3 cell, or maybe a 5 cell battery, 4 cell battery. So 3.3 volt multiplied by 4, so it will be like 13 volt or so. So depending upon numbers of cells you have, your voltage requirement will be different. But if the moment you connect your cell phone, the required voltage for that battery is 5 volt, or maybe a 9 volt, let's say, if it's negotiating with the fast charging. Yeah. Then in that case, this is, I mean, this is Type C. Basically, they communicate with the adapter. So adapter is not a dumb 5 volt adapter. It is a basically a smart adapter. Where the moment you connect the device will start negotiating. So device will tell whether, I mean, the adapter will know whether you have connected laptop, whether you have connected cell phone, and what is the required voltage, and it will automatically set that voltage. So moment you connect the laptop, it will take it to the 12 volt or 15 volt. The moment you connect to the cell phone, it may set the voltage to 5 volt or 6 volt or 9 volt.
That is from that is by communicating through
Yeah.
those data lines.
Yeah. Data lines, so different fast charging chargers have their own standards for communication. So if you look at a Qualcomm charger, they communicate with the data line. So most of them communicate with the data line, but in some cases there may be a real data transfer, and in some cases they just detect with the register value connected at the data port. So that register value itself will tell. So they will just monitor that voltage, and similar to what you do with the low speed and high speed USB. Actually, the register values are different, and that voltage tells whether the port is high speed or low speed. So same way, depending upon what registers are basically, I mean, the data lines are terminated with what value of register. By basically calculating that value, you will know what voltage is required or what type of device is connected. And in some fast chargers, there may be a real data transfer over that data line.
So, and adding, you as you talked about power delivery PD. So that is the reason why it has been 20 volt and 5 amp and not 10 volt 10 amp.
Yeah, correct.
That gives an advantage.
Yeah, because I square R losses, I mean, will kill your efficiency. So yeah, so I mean, as I mentioned, I mean, there could be two reasons of using the higher voltage. One is reducing the I square R losses, and the second reason, the device itself require a high voltage, because there may be a multiple lithium ion cells connected in series, because the capacity required is higher there. So and already again the same thing, when you connect the batteries in series, voltage is higher, then you'll have to always step down, and the current drawn from the battery will be smaller compared to if you connect those batteries in parallel. So again, the efficiency will be better with series connected cells compared to parallel connected cells.
Understood.
And you had a question related to LDO also?
Yeah, the two more questions related to batteries I
Yeah.
have.
Yeah.
So there's if we look into voltage versus capacity profile of a battery, it tells that if I charge it at greater than 1C, then my capacity at a longer term, if I see, it will get reduced.
It will get reduced.
Milliampere hour. If I charge at 2C, then battery capacity will reduced if on the longer term.
Battery capacity will not reduce. Are you talking about the reliability, or you are talking about the the battery discharge time? There are two different things. So
yeah, so okay, well, one thing what I wanted to tell is like generally now we have fast chargers which will charge our mobile phone from 0 to 100 in 20 minutes, 15-20 minutes, correct?
Yep. Yeah.
Then we have to, in order to achieve that, we have to go greater than 1C only.
So 20 minutes charging is for usually they will claim for 50% or 75%.
Yeah.
I'm not sure if anybody is claiming 100% charge in 15-20 minutes.
Okay.
So yeah, so that is basically a marketing trick. For the same reason I mentioned, your battery has a ESR, correct? So if your battery has a, let's say, 100 milliohm ESR and you charge with 5 amp current, then 500 millivolt you will be dropping. So instead of charging 4.5 volt at 100%, your capacity will be only 4 volt at 100% looking like. So the moment you stop charging, then battery voltage will drop to 4 volts. So which means it's not 100% filled up. So in order to make it to fill it 100%, you have to reduce the current. So the moment you enter in the constant voltage mode, then your current will start reducing. So in the constant voltage mode, the time taken will be larger. So basically, the moment you stop or enter from constant current to constant voltage, your battery is not 100% full that time. It may be 80% or 90%. And that rest 20-10% will take much longer time compared to what you have taken to fill the battery to 75 or 80%. And that's why they claim 75, 80% in 20 minutes or 30 minutes, this fast charging. Nobody will say that 15%, the 15 minutes is claimed for 100%, because they know that in the constant voltage mode, it will take a longer time, and then they always basically look at what time you are entering in constant voltage mode, and they claim up to that time only. What is the battery, how much is filled up, that. So this is the one thing. So in the fast charging, obviously you can fill up your battery up to 75-80% very quickly, but rest 20-25% will take a longer time. So that may take another half an hour. So you can say that, okay, if you are able to charge your battery to 75% in half an hour, the rest 25% will also take another half an hour. So your 100% charging may require again up to an hour or 45 minutes or so. So that's the one thing. And in the constant voltage mode also, there are some intelligent techniques where you can reduce that time. But when you compare with the constant current mode, that constant voltage mode will always take a long time to charge.
Yeah, understood. And, yeah. So regarding LU, I had few questions. So generally, in my observation, what I have seen is PMOS.
So yeah, before we go to LDO, one more thing I forgot to mention, that when you charge with the battery with the 4C or 5C, because let's say, I mean, 1000 milliampere hour battery is being charged with 5 amp current, so you are charging at 5C, or 3 amp means 3C. So obviously the lifetime of the battery will reduce. So let's say, because you are stressing the battery by providing the current more than the it is rated for. So the battery will heat up more in that case, and due to that, all the chemical reactions happening inside the battery, your battery may get damaged, or may get basically, I would say the lifetime will reduce. And that's the main reason actually. If you buy a cheaper battery these days, most of the replacement, if you're not buying original battery, let's say Chinese battery, it may not last for more than 6 months or so. And even the cell phone also, I mean, maybe couple of years, after couple of years, you will see your capacity will reduce. So if it was your phone was I mean, a battery was lasting for a day, now it will may get reduced to half a day or so. That is mainly because of the aging factor. And can you mute? There is a noise in the background. Yeah, so you can hear me, huh? Yeah. So but if you look at trend these days, I mean, nobody would like to keep the same phone for more than a year. Most of the people change the phone every 6 months. So they are not much concerned about the, I mean, lifetime of the battery or even the entire cell phone, because they know that nobody would like to have the phone for 2 years or 3 years. So that's why, I mean, it's more like a selling point, this fast charging, even though the battery life is reduced.
So that the trade-off is there.
Yeah, trade-off is always there. People are trying some different techniques to increase the lifetime of the battery, but cell phone manufacturers, as such, they are not very concerned. I mean, nobody wants to have the cell phone battery life to 4 years or 5 years, because they know they will dump the phone after a year or so. Yeah. Yeah, now we can go to your LDO question.
Yeah, so generally, when we talk about PMOS and NMOS LDOs, so PMOS LDOs are like limited. Their minimum VIN, what I have seen is minimum VIN is limited to like 1.7 volts, and where NMOS can go up to low as 1 volt. That
Are you talking about the output voltage or?
No, input voltage. Input voltage.
No, why 1 volt? I didn't understand that.
This what I like when
no,
in
no, if you look
PMOS.
at in the lecture, when I comparing PMOS versus NMOS, I'm mostly talking about the output voltage, not the input voltage. Your output voltage is limited, not the
generally why I was talking is, as in PMOS, its input is itself source. So I can't go as low as I want, due to I need to ensure I'm greater than the threshold.
Correct.
So my point is, how those specific numbers are defined, like why 1.7 volts or 1 volts. That was my question.
See, the main difference between NMOS and PMOS LDO is basically the dropout voltage. So with the PMOS, I mean, you can achieve a very low dropout with the PMOS compared to NMOS. So for example, let's say I want a 1.2 volt output, then you can, I mean, your input rail can be 1.3 volt or 1.25 volt. So you can achieve maybe a 50 millivolt dropout. All you have to make sure the dropout across your MOSFET, PMOSFET, is nothing but the VDS of that. And in order to keep that in saturation, you know that VDS should be greater than VGS minus VTH. So all you have to make sure that VGS minus VTH of that PMOS is basically less than your VDS drop, which is nothing but your dropout voltage. So lower the dropout voltage, the requirement for VGS minus VTH, which is the overdrive voltage, will be lesser. So that's why you can easily achieve a very low dropout with PMOS. On the other hand, when you look at the NMOS actually, so now your basically output is source. So now let's say I want to regulate the output at 1.2 volt, then my gate should be 1 VTH plus 1 overdrive voltage. At least that much higher voltage you require, because your VGS requirement is, let's say, 100 millivolt. Then in that case, VGS in this, sorry, not the VGS, the V overdrive, which is VGS minus VTH, is 100 millivolt, let's say. That's what you require. Then if your source is at 1.2 volt, your VT is 500 millivolt plus 1 V overdrive voltage 100. So 1.2 plus 1.6. So minimum voltage required at the gate will be 1.8 volt. Otherwise, you cannot regulate the output at 1.2 volt.
Yeah.
So your gate will be, in that case, should be boosted actually. So
Yeah.
the drain will be connected to maybe a regular 1.25 or 1.3 volt, same as you have a PMOS. But your gate voltage required will be much higher because of this VGS drop in the NMOS, which is not there in case of PMOS, if you look at it. So that's why in most of the cases, if your dropout is very large, and you can still use a NMOS without boosting the gate. So for example, let's say I want to get a 1 volt output with a 1.8 volt input, then your dropout voltage is 0.8 volt, and you know that 0.6 plus 100 millivolt, so 1 plus 0.7, so the gate voltage required will be less than 1.8 volt. So your error amplifier can be powered with 1.8 volt. But if your dropout voltage is very low, in case of NMOS, you have to boost the gate voltage, which means your error voltage, error amplifier cannot be powered from the same rail, but it will require a boosted rail. So that is the main difference between NMOS and PMOS.
Is
that clear?
Yeah, when dropout voltage is higher, we don't require any additional bootstrap or charge pump circuit to boost it. Yeah.
So and NMOS LDOs have certain benefits like a higher PSRR, better transient response, that I already talked about. So sometimes even there is a overhead of a charge pump, you may still prefer NMOS LDO. And another reason is if you look at the overall area, the PMOS mobility is much lower compared to NMOS. So the device size required may be a 3-4 times compared to NMOS. So overall area impact may not be that big. So the area of NMOS regulator may still be comparable with PMOS, and you are able to achieve a better performance in terms of PSRR and transient response.
It's W by L will reduce due to higher mobility.
Yeah.
Dr. Qadeer, can you explain the error amplifier part one more time? Sorry, I missed that point.
So error amplifier is driving your gate of that NMOS. So if my input, the drain of the NMOS is connected to, so let me just draw here. So this is my error amplifier, and you're feeding back here, and let's say this is your rest, and this is your V in, and this is my, let's say, VNH, I will say, higher voltage, and this is my V out. So let's say this is required is 1.2 volt. This is 1.3 volt. So your dropout is 100 millivolt. Now this voltage required will be V gate. So from source is connected to 1.2 volt, which means this should be one dry voltage, and dry voltage, you know, will be minimum to keep in saturation will be 100 millivolt. So VTH plus V drop. And if you consider, let's say 0.5 volt, so 0.6 volt plus V out. That will be the required gate voltage. Because your VGS required is 6, the gate to source voltage required is 600 millivolt. And since your output is connected to 1.2 volt, so that gate voltage required will be 1.2 plus 0.6, 1.8 volt. So if this is, and this is being powered through this amplifier, so this voltage should be greater than or equal to 1.8 volt. So from 1.3 volt, you have to boost and generate this 1.8 volt. Otherwise, you cannot achieve these specs with this NMOS LDO. But if your dropout voltage is more than this 0.6 volt, then you don't require this. So for example, let's say this rail was 1.8 volt V in, output is 1.2. So your VDS here is 0.6 volt, and the gate voltage required will be your V out plus that. So again 1.8 volt. So in that case, both error amplifier and V in can be powered. Or on the other side, if your V out is, let's say, 0.6 volt less than V in, which means if V out was 0.7 volt, in that case, your this required voltage would be 1.3 volt, the error amplifier gate voltage, and then again you don't require. So you have to see what is the dropout voltage, whether dropout voltage is more than your the required VGS or less than required VGS. So if it's more than required VGS, then you don't need boosting. Otherwise, you will require to boost that gate voltage. Is that clear?
Yes.
Okay. Okay, next question.
So I had one more question on the Miller effect. Like
Yeah.
if you take the same image, then if you remember that you drew a capacitor from gate to output,
Yeah.
and you drew two current directions, one which is causing a Miller effect,
Yeah.
and another direction which is causing a right half plane zero.
Yeah.
So I was not able to get that how current direction from gate to output will create a right half plane zero from gate to drain in a PMOS.
No, so look at a high frequency. So if this is your PMOS, this is your capacitor, and let's say this is your V control, and this is your V in. So this is your basically, I would say, I out current. So this current has two components. Okay, one is your this feed forward, correct, and another one is this, and that's what I talked about. So at high frequency it will get shorted. So from here to here, so you want this component to dominate, because this has an inversion from here to output, correct? If this is your V out, so from VC to V out you have an inversion, because this is acting like a common source amplifier, and common source amplifier, you know that if you write the transfer function, it will have a minus term there, correct? So whatever you apply at the input, the output will be out of the phase, 180 degree out of the phase.
Okay.
Correct. But this path is in phase with this input. So if this becomes dominant, your output and input will be in the same phase, and that's what creates the right half plane zero. So overall transfer function you have derived, it has an inversion. But if that minus term is gone, you create a positive feedback, and that's what makes your system unstable. And so that's why if your this component becomes very dominant and that zero comes inside your
Bandwidth.
UGB bandwidth, then it will convert your negative feedback system into a positive feedback system, and it will make it unstable. So that's why you never want this feed forward part to be stronger. You always want this, and that can be limited by adding a series resistor. The moment you add the series resistor, higher the resistor value is, lower will be this current, feed forward current, and you can basically control that zero. And if you make it very strong, then it will maintain the inversion. At the same time, you will get a left half plane zero. So your right half plane zero now has moved to the left half plane, and you can even design a very higher bandwidth. So basically you can use that zero to cancel the pole, left one of the high frequency poles, and you can achieve a very high bandwidth. So that's what you do in the feed forward compensation, pole zero cancellation basically.
Okay. Yeah, I got some idea when to look into further, because I'm not from a VLSI background, so I need to check it. Sure.
Yeah, I mean, intuitively, that's why, I mean, sometimes with the mathematics, you may find difficult, but intuitively, you can understand this way, that there is a inversion between input and output, and you want to maintain that inversion in order to keep your system stable, because it's a negative feedback. But if that inversion, basically that inverting stage becomes a non-inverting stage, then your whole entire feedback system will convert into a positive feedback system, and it will make it unstable. And that's why you don't want to lose this inversion by making this capacitive path stronger.
One last question I have here is, generally some of the parts, when we look into the linear line regulation of the part, some show a positive droop where your V out increases with increasing V out. And some parts, other parts will have a negative droop where your V out will decrease as V in increases. So like you told, like that will be a design thing, but exactly what we will be making in order to behave like that? And
I mean, it all depends actually. So for example, let's say you take the case of this PMOS output stage, okay, or NMOS output stage. So if you have a channel length modulation, I mean, if you are from a VLSI domain, then you will understand what exactly the channel length modulation is. So basically, if you're ideally what you want, you don't want your output to be dependent on the VDS. If your device is in the saturation region, then your current should be independent of your VDS. It should only be controlled by the VGS, which is the gate of the device. So, but you in the line regulation, what happens? You are changing this V in. So if you are changing this V in, which means you are changing the V drop. So let's say instead of 1.3 volt, you make it 1.8 volt. Your output remains at 1.2 volt. Then this 100 millivolt dropout will become a 600 millivolt. So channel length modulation, due to channel length modulation, there is some dependency on the output current. So this current will increase, and then that may cause a change in the output. So that will basically determine. So if your output impedance from drain to source of this, or source to drain of this PMOS is infinite, then your line regulation will be very good. Ideally, there'll be zero delta change in the output with the some delta change in the input. And so in that case, your line regulation will be very good. Another thing, due to this change, this VDS change, I mean, there may be a possibility of changing in the gain of the output stage. So when the gain changes, overall loop gain will change, DC loop gain. So your error in the output will change. So that may also determine your line regulation in that case. So if your gain is increasing, then your line regulation will improve. If your gain is reducing, then line regulation may degrade in that case. So you have to look into both aspects. So one is the VDS, other is the loop gain. So So what parameter is dependent on your Vin, that will determine your line regulation.
Yeah, I got some ideas. Yeah, understood.
Okay. Okay, any other question? So we have, 10 more minutes. If you guys have any question, you can ask. Even if you have any random question, you can ask. That's not a problem.
Okay. So adding to that, sir, one more thing I have, like generally in literature, any data sheets which we see, generally they show PMOS as a low noise LDOs. Generally they market saying that low noise LDOs PMOS. So how that is possible? Because it's how PMOS will provide low noise compared to NMOS. That is what my question is.
So for that, you have to look at the noise aspect of the devices. So the flicker noise, which is a low frequency noise, is always less in PMOS devices. And I mean, this may be due to multiple factors, but mobility also plays one more factor, because mobility is lower. So when the mobility is lower, your noise, even the thermal noise also may be lower in that particular device. So I mean, it's an inherent property of the PMOS device that it's less noisy compared to the NMOS, and that's why most of the time we prefer PMOS with respect to NMOS for low noise application.
Okay, so flicker noise in sense.
Flicker noise is the low frequency noise, which basically you can say that I mean, you have a ultimately everything is driven by your current, and current is driven by the charge. So how those charges are behaving, so they have a low frequency component and high frequency component both. The noise is a random thing. Okay, so so most of the time when you say a random noise, it may have a two components, low frequency and high frequency. So high frequency component is mostly a thermal noise, which is due to maybe collision of the charges and all those, it creates the heat, and that creates your thermal noise. And then low frequency noise is a very slow movement noise, you can say. So which is a very slow change in the current in the device, or charge movement. So that is called the flicker noise, and that noise is lower in PMOS compared to NMOS. It's an inherent property of the device itself. So if you want to understand more, you have to go into the device physics of that particular device.
Okay. So here we are more concerned with flicker noise because it is in low frequency. Thermal noise, anyhow, high frequency.
Thermal noise, as I mentioned, also may be lower in PMOS, because mobility is less. So if your charge mobility is less, the created heat may be less. In that case, your so overall noise in PMOS is less compared to NMOS. But the flicker noise is definitely significantly lower in PMOS compared to NMOS.
Yeah. Thank you. That's
Yeah.
okay.
Okay, if there are no more questions, maybe you guys can at least give some feedback on the overall course. Was it informative or not, or if I have to make any changes in the content or anything. So usually, I mean, the contents I have kept is so that both beginner as well as people who work in the industry, they can both can benefit. So that's why I cover some advanced topic as well as the very basic stuffs here. In future, we may be introducing a advanced level course where it will be more specific to people who already have some background in power management. So, and it will be good to get a feedback so that we can improve. I mean, the contents. Let's say if next year is also being offered, if people want to make any changes in the content, we can do that.
Dr. Qadeer, I'll just make a one comment on that, as you mentioned. So definitely the way you explain and the content is very, very, very aligned with the industry as well as very good for the beginners as well. I'm really fortunate to have those lecture notes. Just only one thing as a feedback, I'll definitely suggest that if you keep some section on the PDN, the power delivery network, where most of the time the load is much away from the our DC-DC. So
okay, you mean
PDN,
the point of load kind of thing?
Yeah, the PDN network loss, like in your
so
as like for server applications.
No,
or in
I
the client.
understand that. So
Yeah.
So usually what happens, these are usually not covered as a power management design aspect. These are optimization which you've done at the system level, correct? So so these are mainly related to kind of IR loss analysis which we do, and most of the time it's a part of the backend actually analysis what we do at the system level. So so that's the reason. I mean, that is not going to affect your core design of a regulator. It's this kind of optimization are done at a system level, which is completely out of the scope of the regulator. I mean, the best you can do, if I want to regulate my load is far away and I still want to get a very good accuracy in the regulated voltage, then we already talked about the local feedback and remote feedback. So those are the techniques which may affect your regulator design. But as such, if you want to reduce the IR drop and all those, because I mean, a power management designer has no control on that. I mean, where the load is being put and where the regulator is being put. I mean, I would always like to prefer load next to the regulator, but at a bigger system SOC, it's not possible. So and that's why if you look at it, it's a entirely, I mean, a new kind of a job which is being done by backend designers, this IR analysis, just like they do all the other analysis at a chip level when they do place and route and all those things. So in the back end, they do a timing analysis and all those. So IR analysis is another part which is somehow related to the power, but it's outside the control of the regulator. So that was the reason I mean didn't cover that because it's just optimizing your resistance, how you route the lines, how you place the place your modules. So for example, if I have a one regulator which is powering to maybe a multiple modules, so I would like my regulator to be at the center of those, so that those modules are surrounded by, so that I can reduce the IR drop rather than putting the regulator at one corner and the other modules at the other corners. So
other end.
Yeah. So that's why I mean I mean, even if I add that, there'll be a I mean, I would say it will be a completely off topic from the power management design point of view.
Okay, I got it.
Yeah.
And with your permission, can I just ask you one quick questions?
Yeah, sure.
If you allow. So just the question is regarding on the board level. So it's so whenever we have a DC-DC and most of the PMIC we have like 4 or 5 rails. So it's very difficult some of the time to place input cap, output cap, and inductor all in the same layer. So the question for you is this. I just want to take your feedback. Which will be the good idea? Like, I have my IC, and as I can't put all three components in the same layer. So option one, I can place my inductor and output cap with the same layer with the IC and take it back the input cap on the bottom layer. Or option two, where I keep my input cap in the same layer with my IC and take the inductor and output cap on the bottom layer.
So
the
so the fundamental rule I have already talked about, you have to reduce the loop inductance, correct? So wherever you have a di by dt noise, and you know that in the buck converter, your di by dt noise is coming at the input side, because that's where your switches are placed. So your current will be changing from 0 to 1 amp kind of a thing within no time, correct? So so there, if you even a small inductance will increase, provide a large change in the voltage, and your devices may get damaged actually. So if your ringing is quite large, and EMI is the another issue which may happen. So the fundamental rule is reduce the L in if your di by dt. So first thing you have to figure out which loop has a basically, or which path has a most di by dt signal, or whatever the component, and which path has the most dv by dt. So dv by dt will affect your basically wherever dv by dt, you know that capacitor becomes more important. So for example, your switch node. So switch node is changing from 0 to VDD all the way. So at switch node, you would like to reduce the cap. Otherwise, what would happen? Your losses will be used at that node, switch node. So your additional switching losses will occur at switch node if you keep adding the capacitor there. So because the dv and di by dt noise, you know, at the input rail, and that's why the important capacitor becomes important. Not the output. If you use a buck, then it is just exactly opposite. The output cap becomes more important than input cap. So so in case of buck, my first concern would be your basically LDI by dt noise. So for that, I know I want to reduce L, and my di by dt path is the input path. So I will always give a first preference to the input cap. Now, at which layer you are going to put, whichever layer is going to provide you the minimum L, just use that. That's it.
Okay, so that di by dt, it's if it is having the small loop inductance, and because of that di, if I consider the peak current mode, so that is it going to be happen that the moment I have high di dt, it will hit the peak, and my it will be either trigger the overcurrent, or it will trigger the high side FET off?
It may not trigger the overcurrent, because you, let's say, I mean, you already have the current limit inbuilt in your device. So and the moment, let's say, your device reaches 1 amp, you will reset your duty cycle. So the problem is happening because of that turning on of the switch, not the current limit. Forget about the current limit. It's mainly because of the turning on and off of the switch. And since that switch is carrying a very high current, and if you have an inductance, what would happen? Your LDI by dt will be the voltage across that inductor. So if your L is higher and di by dt, already you know that it's maybe 1 amp per nanosecond kind of a thing, correct? In 1 nanosecond you can charge. So now, so there could be two ways. Either you reduce your di by dt. In order to reduce your di by dt, you will have to slow down your switching behavior, which means you'll have to basically turn on your FETs very slowly rather than changing. So but then that will, because of that, your dead time will increase, and increasing dead time means you will again incur switching losses. So and your FET will remain in basically transition region for a longer time. If it's changing slowly your gate voltage, then IR drop across that switch will be higher. So I mean, making that simply changing the rise or fall time of that switch will reduce your LDI by dt, but on the other hand, you will have some impact on the efficiency. So the only way here is to you is I mean remains with you is reduce the inductor as much as possible. So that's why we try to basically just make sure in the board layout how we can minimize the resistance. And you know that resistance will increase if your traces are longer.
Yes. Correct.
And then if you are, let's say, chip is on the top layer and your input cap is in the bottom layer, you have to add the vias. So vias will have its own inductance, and then again it may increase your loop. So the best way would be like for input cap to have on the same layer where your chip is. But in case, I mean, due to some reason, your traces are getting longer at the top layer, but at the bottom layer, your traces are shorter, then you will choose the bottom layer over the top layer. So all you have to look which one is giving you the minimum inductance. That's it.
Correct. So I just that is a very good point. So what we are doing right now on the industry side, we are for the inductor, we are making the trace little bit wider.
Yeah.
So that's why we are reducing the R and
Yeah.
try to achieve the higher efficiency.
Yeah.
And because of that reason, what we are doing through via, we are taking the input cap on the back side, because
Yeah.
definitely the via is giving some loop inductance, but compared to efficiency trade-off, it's means that much of cost we can bear. Means it's just the way you mentioned completely. I agree, and that's why I'm trying to identify which will be the best trade-off in between the giving the priority to the DIDT or giving the priority to the efficiency to achieve little more higher efficiency, reducing the DCR.
Yeah. So for the inductance, I mean, the inductance of the traces is not important because it will come in series with your main inductance. So for example, you are having a 1 micro Henry, even if you add a 10-20 nano Henry, it will hardly make any difference. So your R will become more important because that is carrying all the current.
Yeah.
So obviously you would like to minimize your, and I mean, because we are trying to reduce the DCR of the, I mean, we are having these large FET switches, their RDS on is quite low. And if let's say I have designed my FETs to keep the RDS on of 50 milliohm, and in that case, even if you add a 10 milliohm extra, that becomes significant. So your conduction losses will have a huge impact due to that. So you will get a definitely efficiency impact. So whatever the high current paths are, you always try to minimize the resistance. And on the switching side, wherever you have a higher di by dt, you try to reduce the inductance. And where you have a high dv by dt, you try to reduce the cap. So these are the three thumb rules you always need to follow. And now, depending upon how the placement and how you are basically designing your board, you can decide so that you can achieve a best performance on all the three aspects: low di by dt, low, I mean, dv by dt noise, and then at the same time lower I square R losses.
Makes sense. Makes sense. Thank you once again. I really appreciate the way you explain and the way your lecture notes you show all the diagrams. So very helpful for all of us.
My pleasure. Yeah. So, and even if you guys have any question, I mean, don't hesitate writing me directly. You have my email IDs. You can write even after finishing this course. I mean, once you are done with this course, in future also, if you have any questions, you can write me. I will definitely respond.
Very helpful.
Okay. Okay, so if no more questions, then we can hang up. So,
sir, as you talked about advanced course, when can we expect it?
It all depends. I mean, I haven't even started yet. So, I mean, it takes a while. I'm quite busy these days. So with other stuffs, maybe next couple of years. And so I mean, one feedback I want, let's say, if I have to, you guys, I mean, as of today, there is no, I mean, a power management textbook as such, which you can refer. So what I was planning, my first priority, I mean, before I go to advanced level, I want to basically write a book which can be referred as a textbook in the institute, as well as can be referred by the industry people also. So and since my lectures, if you look at the contents, are more or less targeting both industry and institutes. So do you guys think that if I have a same contents in the book, it will be good, or in the book you want to see something different?
It would be great, sir, because in that case you can add more about multi-phase converters where we are using for processes.
Yeah. I mean, some advanced. I mean,
Correct.
what you will see, all the basic stuff will be there, which
There,
I'm
Correct.
teaching in there. There'll be some advanced level also there. So you can say, and when I say my advanced PMIC course, most of the component will be there in the book. So I want to have I mean, I don't want to write 2 books actually.
Okay.
I want to write a single book which a beginner can refer, industry people, or even experts can refer. So
Correct.
there'll be a multi-phase technique, all the advanced techniques everywhere there. So maybe you can say that, okay, 75% book will be based on the lecture what we have, and there'll be 25% addition from more advanced level stuffs.
Correct. That would be great.
Okay.
I will say, Dr. Qadeer, I followed couple of books starting from Erickson or Sanjay Maniktala. So there are a lot of books I followed.
Yeah.
But the way you explain the course content and the way it's aligned, starting from quick idea about the LDO, then you go start deeper on the LDO side. Then you talked about the control loop. Then you cover the buck boost, LCD, then battery charger. So in short, definitely this content is very aligned what we need. And even in the NPTEL side also, there are a lot of power converter lecture, but your course content is the most appropriate what we are doing on the industry.
Yeah, I mean, the reason here is actually, if you are, let's say, somebody is teaching you PMIC or any course first time, if I start teaching you right away from, let's say, stability, then nothing will get into your hand and in headache, basically. So, I mean, whenever you are teaching to someone, you treat that he's a new guy, he knows nothing actually. So when you start from the basics, then he will start picking up the things. I mean, you may be aware of that, but I mean, you may have studied few things maybe 10 years back when you were in the college, but after going into industry, you know, I mean, you are completely off from the theory, so you may not even remember those things. So it becomes like a good refresher for those people also who are expert in the industry in their respective fields. But they want to learn from basics actually, and that's what creates the interest, makes a difference between what subject you will be interested in, what not. I mean, if somebody teaches me a new subject which I am not aware of, but it starts from the, let's say, assuming that I know all the basics, then I may lose the interest in that subject. And that's why most of the books are written. If you look at the Erickson book, they mostly talk about the modeling stuffs. There is no as such a circuit design aspect in that. So if you want to learn the modeling, maybe that may be a good book. But if you want to design a converter, you will hardly get the stuff. So that is mostly targeting the power electronics guys who do a board level design, where they use a discrete controller, power feds, everything. So and even it doesn't cover the all the board level design aspects also so mostly I would say a mathematical book, modeling stuffs it talks about. There are other PMIC books we talk about design, but then they directly jump into the very advanced level stuffs and they don't teach the basic stuff. So that's why there is no single book as of today I have found which you can refer and get all the contents there basically.
I
And
agree.
I don't want to keep a 4 or 5 books every time and just keep flipping the pages if I want to know anything about a particular stuff.
No, I will definitely suggest, Dr. Qadeer, you should think about this option seriously. So we all will be fortunate. Along with your lecture notes, the books will be really good guideline.
Yeah. Okay, great. So I mean, I have already started working on the book, but it's moving slowly. So hopefully in next couple of years, you will see that book will be available in the market actually.
Yeah, really looking forward to it, sir.
Yeah.
Thanks.
Okay. Thank you guys. So
Thank you, sir.
we'll just stop here. And if you have any other questions, you can write to TAs or write to me directly.
Thank you. Thank you, sir.
Okay. Bye.